Okay, I'd like to do a quick review of exponential and logarithmic functions. So all the exponent laws and log laws are listed there, but we'll review some of those as we go through these examples. So the very first thing I just want to talk about is what is an exponential function. So an exponential function is a function in the form of y equals c to the x, where c is a constant, c must be greater than 0, and c cannot equal to 1. And of course, we've got a variable x, so it makes it an exponential function. So what I'd like to do is just draw quickly a growth equation, okay? And a growth equation, something like y equals c to the x, where c is greater than 1, okay? That would be a growth equation. So something like y equals 2 to the power of x, okay? Of course, if we multiply 2 times itself, right, 2 squared, right, if x is 2, 2 squared would be 4, 2 cubed would be 8, and so on. So we can see that when we multiply c by itself, however many of times, x many of times, we get a growth function, okay? And our y-intercept there is a 0, 1. Okay, we've got 0, 1 because when x is 0, right, 2 to the power of 0, anything to the power of 0 is equal to 1. So there's our y-intercept, and of course we have a horizontal asymptote right here on the x-axis, okay, which is the equation y equals 0. All right, so that's a little bit about the growth, and then of course we have the decay function. Okay, again we're going to have a asymptote at y equals 0 along our x-axis, but instead of a growth function, okay, we would have a decay function. So what would cause a decay function where y is equal to c to the x, where c is between 0 and 1? So for example, something like y equals 1/2 to the power of x, right? If I multiply 1/2 by itself, if x is 2, for instance, 1/2 squared would be 1/4, right? So when we multiply a number between 0 and 1 by itself, right, when we multiply a little number less than 1 by itself, then we get a smaller number still, okay? So the numbers are decaying. And still the same rule follows that if x is 0 here, y would be 1, right? Because anything to the power of 0, 1/2 to the power of 0 would be 1. So there's our y-intercept. And this is what we call a decay function. And of course, here's our basic function, y equals c to the x. And we can take that function and we can transform it with all of our transformations from our first unit, which we'll look at in the next example. Okay, one thing we know is that we know for a log function is simply an inverse of an exponential function. So if we had something like y equals to 2 to the x, and we switch x and y, we would get x equals 2 to the y, and when we change that into logarithmic form, we get log of x to the base of 2. So our y equals 2 to the x, which would have had a y-intercept of 0, 1, and a couple points of, -1 and 1/2, and 1 and 2, and 2 and 4, and so on. When we take the inverse and we reflect that over the line y equals x, 0, 1 becomes 1, 0, -1 and 1/2 becomes 1/2 and -1. So that would be 1/2 and -1, and 1, 0, and 1, 2 would become 2, 1. So we've got a couple of points there, and our growth function, our exponential growth function, looks like this as a log function. So that's y is equal to log of x to the base of 2. Okay, and the same thing with a decay function. Okay, that decay function would have started up here, and of course we're decaying, so we're getting smaller and smaller and smaller. So there would be, for example, y equals 1/2 to the power of x. and the 0, 1 would still become 1, 0, and our graph would look something like this. Okay, so that would be y equals log of x to the base of 1/2. Now, a couple things to note. Okay, line of reflection, y equals x. The invariant points are about that line of reflection. So see, that one just kind of worked out the way I drew it. I can't always draw it that perfectly, but it worked out. So there's that invariant point, okay, on the line y equals x. There's our IP. Over here, there's no IP on the left-hand side because, of course, there's nothing that touches the line y equals x, but that's the line of reflection. So there's just a brief sort of intro or review of what those log functions look like. And of course, we can transform those just like any other function, which we'll do on the next page. Okay, so what I've done here quickly is I've just sketched for this graph the original identity function here of y equals 3 to the x. And I know it was the base of 3 because, of course, my base of my log function right here is 3. So I sketched that really quickly, and I just put some points in a table of values so that we can take and map those points when we graph this new function. So it says use transformations to sketch the graph of the function y equals 2 log base 3 of negative x plus 1. So one thing I remember right away is I need to factor out this value here, which we call the b value. Okay, so we're going to factor that out first. And so we get y is equal to 2 log of negative 1 x minus 1 base of 3 there. And so we can see right away that we've got a vertical stretch by a factor of 2. Okay, we've got that vertical stretch by a factor of 2. That's our only vertical change. So in terms of mapping, we're going to multiply our y values by 2. And our x values, we've got a horizontal reflection, which will cause us to multiply our x value by negative 1. And then we're going to move right 1. So in terms of our mapping, we're going to go negative x right 1. We multiply that x by a negative 1, and then we move it right 1. So that's going to be plus 1. And then our y value would be a 2y. So if I take some of those points in my table, we have got the negative 1, 1/3 will become 0, right? Negative 1. Let's just write it right out here. We'll go, it's the negative . Okay, for this next question, it says use transformations to sketch the graph of the function y equals log 2 log base of 3 of negative x plus 1. So one thing I notice right away is I need to factor out this negative out of that b value. So I'm going to rewrite this as 2 log base 3 of negative 1 x minus 1. I have to factor that negative 1 out of there. Now before I moved on to this question, what I did is I quickly just found points on the original function of y equals 3 to the x, right? This is the log function that's been transformed, but my original points would have been negative 1, 1/3, 0, 1, etc. And I know that the inverse, being the log function, my original log function, would have had the points of the exact opposite. So those would have been 1/3, negative 1, 1, 0, 3, 1, and 9, 2. So what I want to do is I want to map those points and switch those. I can see that I've got a vertical stretch by a factor of 2, so that's my only y sort of operation. And then in terms of our x, we've got a horizontal reflection, so we're going to multiply x by negative x, and then we're moving right 1, so we're going to add 1. And then, of course, our y will be 2y. So if I take my point 1/3, negative 1, that's going to become a negative 1/3 plus 1, and 2 times negative 1, which will give us which will give us 2/3 and -2. And if we take the next point here, I'll just sneak it up here, 1 and 0. It's a negative x, so that's going to be a -1 plus 1, and 2 times 0, which will give us 0, 0. And if we do the same thing with 3, 1, we get a negative x, so a -3 plus 1, and a 2 times 1, which will give us a -2 and a 2. And our last point that I have here, 9, 2, we get a negative x, which is -9 plus 1, and a 2 times 2, which will give us -8, 4. And so now I just want to go over to the graph and I'm going to plot those points. I also know that because my graph has moved to the right 1, okay, the graph has moved to the right 1, even the asymptote will move right 1. So where my asymptote was here at the y-axis, my asymptote was the y-axis, my new asymptote, our new asymptote is going to be here at x equals 1. So I'll just draw that in right there. And so now let's just plot those points. Those new points, we've got 2/3 and -2. This is approximately there. We've got 0, 0. A new x and y intercept, -2, 2. And -8, 4 would be out here somewhere. So we can see by the sketch of these first 4 points that we've definitely stretched vertically, twice as tall, right? Our graph is twice as tall. It's moved, it's reflected to the left, and it's moved right 1. So the equation of the asymptote, the equation of our asymptote there is x equals 1, which we've already labeled. Our domain would be from -infinity to 1. Oops, and of course those are both round brackets. The y-intercept is of course at 0, 0, and there's an x-intercept at 0, 0. So we've just transformed that function. All right, let's move down to the next question. So what we want to do here is we want to write each expression in terms of individual logarithms of x, y, and z. So we want to split those up, is what we're saying. So we can rewrite this first a as log of x, y to the power of 1/2 to the base of 5. And that half applies to both of those, x and y. So we can rewrite this as x to the 1/2 to the base of 5 plus log y to the 1/2 to the base of 5, which is totally fine and correct, but usually, remember, we're going to take this exponent and we're going to bring that down. So that would be 1/2 log of x to the base of 5 plus 1/2 log y to the base of 5. And question B. So we've got our product law and our logs of multiplication and logs of division. So what we're going to do here on the numerator, we're going to rewrite it as log x to the 5 to the base of 6 plus log y to the base of 6. Subtract, let me just scooch this down here, subtract log of z to the base of 6, log of root z to the base of 6. And of course that root z, this first one, the 5 is going to come down, 5 log x to the base of 6 plus log y to the base of 6 minus, we know that z, square root of z is z to the 1/2, so that's going to be minus a 1/2 log z to the base of 6. And now we want to go in the other direction. We want to write these as a single logarithm. And of course, we're going to multiply the log xy to the base of 3. And this next one is log of x cubed to the base of 2 divided by y squared, right? This 2 comes up here, and times z to the power of 7. Okay, a couple of review questions for the laws of logs. Okay, so let's look at some log applications. The first question says, one earthquake measured 9.5 on the Richter scale, and the second earthquake measured 7.6. How much more intense was the first earthquake than the second? So the intensities come from 10 to the power of the Richter scale. Okay, so our first earthquake was 10 to the power of 9.5, and the second earthquake is 10 to the power of 7.6. So to compare those intensities, we would divide to see how many times more intense was the first one. And of course, when we divide powers with the same base, we're going to subtract those exponents. So 9.5 minus 7.6, which is 10 to the power of 1.9. And if we just pop that into our calculator, the first earthquake was 79.4 times as intense. Okay. Now for question B, it says a major earthquake of magnitude 7.5 is 375 times as intensive as a minor earthquake. So we know that 10 to the 7.5, some earthquake, when I divide their intensities, we get 375. And the second earthquake, we don't know what the intensity is. So again, we have division of powers with the same base. So I'm going to subtract. So we get 7.5 minus m is equal to 375. So now this is an exponential equation that I can't solve by changing to a common base. So I'm going to take the log of both sides. And I get 7.5 minus m log 10. I need brackets around that. Equals log of 375. And now, of course, log of 10 is simply equal to 1, so we can ignore that. And when we move this minus m over, and we move our log 375 over, we get m is equal to 7.5 minus log 375. And if I just plug that into my calculator, I get 4.9. Okay, so the second earthquake had a magnitude of 4.9 on the Richter scale. Okay, so for this third question, it says a whisper of 30 decibels is how many times as loud as a conversation of 60 decibels? So the trick with the decibels is that one bell is equal to 10 decibels. So we can actually now, because we have probably better equipment, we can pick up sound and break up the sound into smaller units called decibels. But when we do the comparison, we need to convert to bells. So a whisper of 30 decibels, that would be 10 to the power of 30, compared to a conversation of 10 to the 60. Well, if I'm going to compare this, I need to subtract, of course, still. So 30 minus 60. We need to divide by 10 to convert to bells. So we've got 10 to the power of negative 30 over 10, which is 10 to the negative 3, which if we rewrite that as 10 cubed, 1 over 10 cubed, that's 1/1000th, which makes sense because a whisper of 30 decibels, a whisper is, of course, not louder, so it is 1/1000th as loud. 1/1000th times as loud. All right. And the next thing we want to look at is some exponential and logarithmic functions. So this very first equation, this is an exponential function. And the first thing I always want to do with an exponential function is try to change to a common base if possible. So this first one, I'm going to rewrite 27 as 3 cubed to the power of x minus 2 over
equals 1 over 3 to the power of 4 to the x plus 1. Or sorry, to the x plus 3. And now let's expand. So we get our 3 to the power of 3x minus 6. And we could change the 1 to 3 to the 0 if we wanted. Okay, there's a couple of strategies there. So that's a 3 to the power of 0, we can say, which is 3 to the power of 4x plus 12. And now this is 3 to the 3x minus 6. And then 3 to the power of negative 4x, 0 minus 4x, and 0 minus 12. That's negative 4x minus 12. And now my bases are the same, so I'm going to drop the exponents. So 3x minus 6 is equal to negative 4x minus 12. And I get 3x plus 4x, which is, of course, x. I'm just going to move the negative 4x over. Right, when we move that negative 4x over, that's, of course, a plus 4x. And the negative 6 becomes plus 6. And so we get 7x is equal to negative 6. So x is negative 6 sevenths. Another thing I could have done mathematically, I'm just noticing, is instead, just as an alternative, some of us might be thinking, why didn't I do it like this? I could have also just thrown this over 1 and then cross multiplied, because that's, of course, a proportion. So I could have rewritten this like 3 to the power of 0 is equal to 3 to the 3x minus 6 times 3 to the 4x plus 12. And then I would still, 3 to the 0 is 3 to the 3x minus 6 plus 4x plus 12. We'll get the same answer there, but I wouldn't have to deal with as many negatives, perhaps. So we get 7x plus 6 here. And of course, negative 6 is 7x. So again, we get the same answer, negative 6 sevenths, just in a slightly different algebraic approach there. Okay. For question B, what I want to do is, again, I want to try and change these to a common base, but I certainly cannot do that. So I want to isolate my power here, 4 to the x minus 1. So we're going to divide both sides by 3, and we get 4 to the x minus 1 is 5. And now, when I can't change to a common base, my strategy is to take the log of both sides, right? Change to a common base, which is what we did over here. Okay, change to a common base, but over here we're going to take the log of both sides if a common base is not possible. And when I take this x minus 1 down, I need brackets, or it's technically incorrect. So we get x minus 1 log 4 equals log 5. And I could distribute that, x minus 1, or we can divide both sides by log 4. We get x minus 1 is log 5 over log 4. So x is 1 plus log 5 over log 4. And now that's my exact value. Sometimes you'll see this written as this, okay, with a common denominator here. I could change that 1, okay, so this is totally fine. I could also sometimes see this written like this, log 4 over log 4 plus log 5 over log 4, which when combined is log 4 plus log 5 all over log 4. So sometimes we'll see that written like that as well. And if you want the decimal approximation, you can plug that into your calculator. So let's look at the next one. So this next one is a logarithmic equation. So what I can do is I can simplify a little bit that left-hand side. Before I do that, let's look at our restrictions. We know that a logarithmic function must always be greater than 0, right? Our argument always has to be greater than 0, or it has to be positive. And so I know the product law tells me I can multiply 3 times x, and that's equal to log of 2. And now I've got a log of both sides, everything's simplified, a single log, so I can drop those logs. Okay? And so what we get, we can equate our arguments. So 3x is equal to 2, divide by 3, and x is 2/3. I'm just going to double check that that's okay, and it sure is. It meets my restriction. Question D, again, I'm going to simplify that left-hand side. So we've got x plus 2 times x minus 4, all to the base of 4, and that's equal to 2. Now, this one, we're going to use a slightly different approach. I don't have logs on both sides. This is a log jam. And how do we get out of a log jam? We change to exponential form. So we get our x plus 2 times x minus 4 is equal to 4 squared. And of course, on our left-hand side here, we're just going to FOIL this. So we get our x squared minus 4x plus 2x minus 8 is equal to 16. So that's a minus 24 equals 0. Ooh, and I just realized we also need our restrictions here. So from this one, we know that x must be greater than negative 2. And from the second one, x must be greater than 4. Okay, so our overall restriction is x is greater than 4. And now when we factor, we get an x minus 6, factors of negative 24 that up to negative 2, x minus 6 and x plus 4. So x is equal to 6 and x is equal to negative 4. But in this case, the negative 4 gets kicked out because x must be greater than 4. So here's our answer. Okay. Exponential applications. So we've got our half-life formula. Okay, and so our exponential equation formula here. So a bacteria culture starts with 5,000 bacteria. After 6 hours, the estimated count is 80,000. What is the doubling period for this bacteria culture? So our little formula here, y equals a times b to the t over p. A, that's our initial amount. That's always our start amount. Okay, b is what we're doubling. It's our doubling or tripling or half-life, okay, etc. T is our actual time. T is time. And P is the period. Okay, it's the doubling period or the half-life time. Okay, how long does it take to break down to half? Okay, and then, of course, y would be our final amount. So in this particular question, a bacteria starts at 5,000, so there's our A value. After 6 hours, so that's T is 6. The estimated count is 80,000, so that's our y value. That's what we end up with. What is the doubling period? So that's our B value. Okay, what is the doubling period? So we're looking to solve for P, aren't we? Okay, P is what we're actually trying to find here for this question. So we know 80,000 is equal to 5,000 times 2, right? B is 2 times 2 to the power of 6 over P. And now I can divide both sides by 5,000. And we know 16 is equal to 2 to the power of 6 over P. Now I could use my calculator for this one, but I recognize right away that 16 is a power. 16 can be written as a power with base 2. So 2 to the 4 equals 2 to the 6 over P. So 6 over P is equal to 4. And some of you remember the little trick that we can just switch our diagonals. So P is 6 over 4, or 3 over 2, or 1.5 hours. I think that's it for the review, and now the rest is practice. Okay, so go ahead and do those questions. If you have any questions or concerns, please do not hesitate to contact me. Thank you.